Okay, so I'm making this video with the understanding that OpenStack's Chapter 12 actually aligns really well with Unit 5. Basically, everything in the AP Chem standards for Unit 5 is within Chapter 12. There's nothing critical to talk about that isn't. But there's just a few MCQ strategies for some of the MCQ problems that I think are worth explicitly going over. So I made a list of the topics. I would suggest that you maybe not even watch this whole video, but just see this list. And if you haven't done the MCQ questions yet, maybe go ahead and do them. And then if you see one of these topics that's bothering you, you can come back to this video. Or if you really want to be super completionist about watching every optional thing I give you, you can watch these, and as you're going through them, I would recommend pausing before I do my MCQ explanations, because these are also MCQ practice problems that are within the ones I gave you that I use as some of the examples. So if you pause me as I'm talking and answer it, then you can see if you already know it, and then you can mark off that MCQ is being done anyways. So hopefully that makes sense. So just 8 different ideas that help to answer these MCQs. The first idea is telling the rate of reaction by looking at a data table. So you don't necessarily need to make a graph to determine the order of a reaction. You can also see which looks linear by having even spacing between values. And we talked about this a little bit in the Crystal Violet lab, how I don't necessarily need to look at zero order, first order, second order, and graph all of them. I can simply say, which one has an equal spacing between the values over time? In other words, which one changes at the same amount? So here I could see 90, but here's only 45. Here's 22.5. Okay, that's not equal spacing between values. Here I have a difference of about 0.7. Here's about 0.7. Here's about 0.7. That's equal spacing between values. And I know that's the first order equation. So that equal spacing tells me that if I was to graph it, that would be linear. And so I can say that this has to be a first order reaction. Okay. Second, multi-step reactions with specifically when the first step is fast and the second step is slow might trip you up. So here's some examples, 6, 47, 64, some examples. So here's my tip for you. If the first step is fast and the second step is slow, then the products of the first step, which are reactants in the second step, are equivalent to the reactants of the first step. Might sound like a mouthful. Let me explain. So if we look at these, for example, number D, or letter D, says, is this the rate law? Well, I'm looking at the slow equation, and I don't see CO here in the slow equation. And the slow step is the rate determining step. So how is that possible? Well, again, you can see that the products of this first step are here in the reactants of the second step. And what this is saying, if the first step is fast, then the products of the first step, which are reactants in the second step, so in this case that is C2O2, are equivalent to the reactants of the first step. So in the rate law, I can write, instead of C2O2, I can write CO squared, because this is equivalent to this. And the logic here is because the first step is fast, the rate of producing the products from that first step and that intermediate is not limiting my rate of reaction. What's limiting it is the second step. Now, I think I included in the slides, if you look at the real slides online, a link to an explanation of this. If you're like, that explanation isn't good enough for me, you can have a college level explanation of why that is, which is kind of difficult and I think more than you need. I would just keep this in mind, that the products of the first step, which are fast, are then used in that second step. You can use the original reactants from that first step in the rate law. So then instead of C2O2, times O2, it becomes CO2 squared times O2. So we just took the products from the first fast step that are reactants in the second step and said those are equivalent to the original reactants in the first step. And therefore D is actually correct. I think this is the most confusing one out of the 8 I'm going over. So here's another example. This is number 47. The experimentally determined rate law for the reaction is the rate equals CO times O2. Which of the following proposed mechanisms is consistent with the rate law? So if we look at number 47, we can see that the first step here in some of these is fast. So I'm just going to skip to the one that's the answer to explain for sake of time. Of course, you could go over the others and see why they're wrong. But B is correct. And why do we know B is correct? Well, that first step is fast. So the 2O, because the O is a reactant in the second step, then we can say that the O, which is a product in the first step, which is fast, is equivalent to the O2, which is a reactant in that same step. So instead of writing O as a reactant in the rate constant, I would write the O2 that is in the formula. So there, I have my O2, and then that is reacting with the other reactant. So it's O2 times CO, and we can see that that is equivalent to the rate law here, so that makes sense. Okay, one more. This is the most confusing one. I think this is the most confusing thing out of these MCQs I'm talking about. If there is another product, then that product you are dividing. And there were some in the OpenStax books, there were some examples of this, which actually the examples in the OpenStax books talk about determining like the new K value and stuff, which I haven't seen any AP MCQ questions go over, so I don't think you need to know that. But you can see that the first step is fast, the second step is slow. So these NH2O minus, I'm going to replace it with the concentration of NH2OH as the reactant. But because there's another product in that previous step, and I think it's just easier to know this than to talk about why. If you didn't understand, if you really want to talk about why, review what the OpenStax book says. But I don't want to get it into, or the previous lessons where I explain the OpenStax book's answers. But I don't want to talk about it in detail here. You would just divide by that other product of that first fast step, which is not in the second step. And therefore, the correct answer here for this one, which is 64, is D, because it's taking that reactant, dividing by the other product. So just remember that you would then divide, if there's another product in that fast step, then you're dividing by that in the rate constant. I would just remember that, but if that's not enough for you, again, you can go back to previous videos in the OpenStax book where that is explained more. Okay, other things, I think the rest of the list is easier. Absorbance and half-life. If you're trying to calculate half-life given absorbance, whatever the starting absorbance is, consider that 100%. So then look, what's 50% of that starting absorbance? And that will tell you, that time length of time will tell you what the half-life must be. Remember, more surface area and catalyst increase reaction rate. Not sure if I explicitly said that in other videos. I think I did, but just keep that in mind because that comes up in a lot of these MCQs. Keep in mind that sometimes AP Chem likes to write the catalyst as a part of the equation. If something is used as a reactant and a product, so like you can see in this example here, Br is a reactant and a product, that means it's a catalyst. So if you see something that starts in the reaction and is produced at the end in the step-by-step mechanism, that means it's a catalyst. Number 6, which is based on 41. Let's say you get a problem like this, and you're like, how do I find what the half-life is? Find the number of divisions that occurred. So it says 87.5% decayed. That means we have 12.5%. That means we have 1/8 left. Well, then how many halves have happened? Well, we went from 1/2 to 1/4 to 1/8. That's 3 half-lives. And if it's in 35 hours, well, then we're going to say, okay, 35 hours divided by 3, because there have been 3 half-lives, and that gives us our 11.6 hours. So you just find how many half-lives have occurred, knowing that the amount left is going to be half of it was before every half-life to determine what the half-life length is. 7. If you need to find an overall catalyzed reaction given the steps of the mechanism, the chemicals that don't cancel out are left in the overall reaction. So something like this, which is number 57, you can see that it's giving us all the steps, and it says, what's the overall reaction? Well, I would look for everything that cancels out. It's like, okay, there's Mn2 plus, Mn2 plus, so that cancels out. Mn3 plus, does that cancel out? Is there another Mn3 plus? Yeah. And then Cu2 plus, yeah, Cu2 plus. CO3 plus, no, that doesn't cancel out, so I'm going to note that. And then Mn4 plus, yeah, that cancels out. Cu plus, yeah, here we go. So all that's left for products is the CO2 plus. So it's going from CO3 plus to CO2 plus. That is the overall equation here. And then there's another chemical, which is the Mn2 plus, acting as a catalyst. So the product is just CO2 plus, and so C is correct for this one. So you're looking at everything that cancels out, and what's left would be the overall equation. The last thing, be comfortable looking at graphs of multiple steps. And so like we're all familiar with, it gives the energy here, and then this is like reaction progression, and there's a hill, and the top of the hill is activation energy. What if it shows you the multi-step mechanism? Well, if it gives you something like this, okay, and then there's like multiple steps, and then the final or whatever's the highest hill, that's the slow step. So just keep that in mind. If it's giving you a multi-step mechanism and asking to identify which one fits, the highest hill must be the slow step. Now I'm looking at this, that looks a little funny. I think that's fine. What I drew there, I'm not 100% sure, but just a little scribble. The only point of the scribble is to understand that the high hill is the slow step. That's why it's slow, because it requires the most energy. So there you go. That is it. Those are my main notes from MCQ. Optional viewing of this if you have questions as you're going over the MCQ problems.